this point, actually, you're not yet done. So what you will wind up doing is you recompute the centroids. Okay? The centroid for red is here, centroid for blue is here now. Now you ask everybody, do you want to change? At this time, nobody wants to change. And so you stop. Okay? Looks like the coolest, cheapest algorithm that you can do. And so everybody, when they have to write a clustering algorithm, the first thing they do is k-means clustering. Okay, so what you'll try to do in the remaining time today and also next class, that is next Thursday, what are the properties of k-means clustering? Okay. Anyways, in this case it's converged. So what k-means is optimizing, essentially, it turns out, remember it's a clustering algorithm. It has to, the only thing that you can try to optimize over is the internal measures. There is no point in optimizing to external measure because, as I said, if you happen to know the answers to the exam, don't write something and check. Just write, copy the answers. That's much more efficient. Right? So the point is, if you are making the clusters and you want to see is this clustering any better than the next clustering, you need to only consider internal measures of consistency of the clusters. And there are two ideas, right? One is intra-cluster tightness and inter-cluster distance. Since I have kept k constant, then I would argue that in some sense, the intra-cluster tightness, if you maximize that, if you maximize the tightness, you also by definition maximize the inter-cluster distance. Because the k is constant. I'm keeping this k the same. So if each cluster becomes closer and closer to itself, then it's also by definition becoming farther and farther from everybody else. Okay? So even though the function is supposed to be a function of both inter-cluster tightness, intra-cluster tightness and inter-cluster distance, actually you can think of k-means as just focusing on the intra-cluster tightness. Now how do you define the intra-cluster tightness? What all you can do is you basically can consider the distance between every point in the cluster to its centroid of the cluster. Okay, suppose I have these points. Remember, centroid in k-means doesn't even have to be a real point. Right? And so, essentially, you have computed the centroid and you're asking yourself, how close are you to the centroid? So, you are, let's say, this is D1, this is D2, this is D3, and so on. Okay? You take the distances, essentially, and you sum those distances. Sum of squares of distances. Okay? So, notice that since this is one cluster, here the distances for the points are with respect to this cluster. The guys here will be looking at their distances from their own centroid. And I take all the distances here, squares, sum of squares of these distances, sum of squares of these distances, and sum them all together. That will give me, in essentially, a measure of tightness of the clusters, of the k clusters. And you can see that k-means, when it goes from iteration to iteration to iteration, it is not, it's guaranteed to not increase this distance. It's guaranteed to not increase this distance, which is, you're computing the tightness as a sum of distances of elements within each cluster to its centroid, right? As the whole point of the iterations in k-means is for you to go closer to your centroid. Go into a cluster where you are closer to the centroid. Right? And so that's basically, you can see that in fact if you actually compute this measure from iteration to iteration to iteration, you can see that it's monotonically non-increasing. Most of the time actually reducing. Okay? And then when it reaches a minimum point, when it no longer, nobody has any incentive to change. Okay? And that minimum may not be the global minimum, it turns out. There may be a different clustering over the same K clusters that might be even smaller, but K-means won't have, K-means with the initial seeds may not have come to it because it's an iterative process. Okay? So the reassignment monotonically decreases G since each vector is assigned to the closest centroid. Okay? Now, other interesting thing is, if you are focusing on considering tightness by reducing, making the sum of squares to the centroid be minimum, what shape do you think will you get? Spheres. High dimensional spheres. What if the clusters that naturally define your data are not actually spherical? You will still find them. Because if it's spheres you're going to look for, you're going to find spheres. Okay? So that's the problem with any clustering method. They have their own inbuilt bias in finding particular shaped clusters. K-means tries to find spherical clusters. And if your cluster, and if you have a bunch of data which is sort of chain data, then K-means is not a particularly good at doing it. Okay. One last thing, of course, is the value that K-means comes to. As I said, this value, this measure keeps monotonically non-decreasing. At some point of time, it stops changing from 2 iterations. Between 2 iterations, if it doesn't change, then you just stop at that point. That means it didn't change because nobody wanted to do it. Right? At this point, can I say that it is an optimal such clustering? I mean, is this the lowest this number could have come across all the K clusterings of this data? Across all the K clusterings of this data. Okay? And the answer is no. And the reality, the reason, and I'll give you an example first, because I'll come back to these things later. But look at, let's see, look at this example. Okay, the problem with K-means is the initial seeds wind up changing the cluster you will eventually get. Okay, so if I have points like this, okay, and if I start with B and E as the initial centers, okay, then I would find A, B, C, and D, E, F as the clusters. As much as in that example, we found that the initial leaders didn't matter, actually they do in some pathological cases, which is why K-means is not optimal. Okay, which is one reason why K-means is not optimal. So if you had picked B and E, you would get A, B, C, and D, E, F as the clusters. Whereas if you picked D and F, okay, then you would get A, B, D, E, and C, F as the clusters. And these two clusterings may not have the same cluster tightness. In fact, one can argue, I think I would say that this clustering is tighter. These 4 together, these 2 together is tighter clustering than those 3 together, those 3 together. But if you started with B and E as the initial seeds, in some sense, K-means would never have found this clustering. Now the question is, why would that happen? And the reason for that is really because individuals are changing one at a time. If individuals can coordinate and change in groups, this problem won't happen. Okay, but from a theoretical point of view, K-means is not optimal. Even for the measure, it's trying to optimize. But it is a pretty good algorithm in general. Okay, the last picture I will show is this. This is on some real data on something antenna data. It's about some measurements on antennas. Okay, over to X and Y axis, and here is the way the data is shown. And if I ask I need to find 3 clusters in it, irrespective of where it starts, it will eventually find the 3 correct clusters. In this, not everybody, not irrespective, I'm sorry. In this case, actually you're showing, I started with this and I'm assuming these are the, let's see, how many clusters are we looking at? They're the circles are the means. And so we actually are looking for 2 clusters in this case. Okay? So suppose I assume that these are the 2 centers originally. And then after one iteration, then this becomes one cluster, this becomes another cluster. And so the centers will change again. Okay? And the centers will change until this is one cluster and this is another cluster, which is sort of what you have seen, by looking at the picture. Okay? And this plot actually shows how the wrongly placed centroids slowly traverse to their correct place. Okay? Generally, K-means clustering is pretty good, and if you're doing it for text data, and if you are sort of thinking, okay, I have 1,000 documents that I'm about to give as the answers to the user, can I then try to look for 5 clusters in it? You will find 5 clusters. And then you can show the user each of the 5 clusters. That actually raises a question as to how do you provide a snippet for the cluster, which we'll talk about it in the next class. Okay? But then if I give you a little snippet on each of the clusters, then you will be able to, you are actually able to give the user the ability to decide which cluster they're more interested in. And then that sort of increases the precision. Okay? I'll stop here, we'll come back and continue this next time.